Okay. Let's get started in today's class. So actually, can find many empty seats. So my TA is actually the TA is previous class, and then they were surprised that there were many class. Okay? But I believe posted the YouTube video, and then I believe that you are extremely hard for exam, right? Good. Okay. The midterm exam we will cover what we are learning in class. Okay. In this class, I will discuss about another building block, another combinational building block. It's called decoder. I will explain about the delays, combinational logic. Okay. Then the midterm will cover the chapter 1, chapter 2, book, and then system value part we learn until today's class. About the multiplexer, it's a very important block, and then we can use the multiplexers like a basic flex. Think about this. When we if else statement, then if else statement that based on the condition of if statement. Okay. It doesn't matter. Okay. Based on the condition of if statement, the execution path can be changed. But we frequently use this if and else statement in our software code. So which means that the hardware also requires the frequent if else statement, and then actually if else statement can be implemented using multiplexer. So which means that based on the selection of the control signal, then we can just select the two outputs. So output is connected to one input to another input. So that is the behavior of multiplexer. So which means that based on the control signal, okay, this is very important. Actually, we frequently use the control signals in the system because, as I mentioned, based on the control signal, then the output can be changed. So we can implement the multiplexers using the basic state or the tri-state, but usually, actually, as I mentioned, that we can use multiplexers like basic gate. So which means that a fabrication company like the TSMC or Samsung and provides the basic block, for these multiplexers. Okay, so we can just connect the. We can just assign multiplexers in our NS system, then actually the input and output ports of the multiplexers are connecting each other, like the basic gate, like AND and OR, and then exclusive OR gate. Okay. So we learned that we can build basic gate, we can build some AND. Actually, we can build any combinational logic using multiplexers like this. So we can use the AB. So it means that the input signals can be connected to the control port of the multiplexer, the selection port. Then we can just connect the input ports of the multiplexer to high voltage in like VDD or RAR. And then we can build the combinational gates using multiplexers. Okay. Okay, let's learn about the decoder. Decoder is the another basic combinational building block. And then actually this is the definition of a decoder. So it's just a definition, so teacher need to memorize. You need to memorize it. You need to know the definition of this decoder. So if we see the this decoder, so we can find that decoder has multiple inputs and multiple outputs. Okay, but we can say that if decoder has n inputs, then decoder will have 2 power of n outputs. 2 to the power of n outputs. So which means that, so this is the example of 2 to 4 decoder. So which means that the first 2 represent the number of input ports, and then the another is 4, number 4 represent the number of output ports. So 4 is the 2 to the 2, okay? So as if the decoder has n inputs, then decoder will have 2 to the power of n port, output ports. Then how can we define the output of decoder based on the input values? So we can generate the two people. So because in this example, this decoder has 2 inputs, so instead we can have four possible values for 2 input ports, like 0, 0 to 1, 1. And then let's see the output value. So in this decoder, the value of input ports represent the position of output bit. Okay, so which means that if we see that this input value is 0, 0, so which means that it's just 0. So in this case, the output, the bit number 0 of output port becomes 1. So which means the output becomes 1 for the input, the value of input ports. So actually we can write like this. So y a equal 1, right? So a is the values of input, a0, a1, so it's a 0. So and then it becomes 1. So which means that it's y0 equal 1. So this, and then for this case, the second row, if we see the second row, so which means that the value of a is 1. So which means bit number 1 of output y equals 1. So this is the definition of decoder. Yeah, why do we use decoder? So which means that why do we learn about the decoder? So we can use decoder for some tri-state gate. So for example, so you know, this is the tri-state, yes. So this is one. So there are 4 tri-state gates, and the output of tri-state gates are connected to the one output. Then we can select the one of these tri-state gates based on the input values. So for example, so we can think that this is the tri-state gate number 0, and this is 1, this is 2, and this is 3. And then we can select the activation of the tri-state gate using the y. Okay, y0, y1, y2, y3, right? So in this case, so these are tri-state gates. So which means that we need to activate only one tri-state gate. If not, y becomes y will include companion values. So which means that y will have incorrect values, so unstable values. So we need to only activate one of these twice the gate. So for this purpose, we can use decoder. So which means that if A is 0, so which means that we can think that the twice gate is 0 is activated. So which means 0, 0, 0, 1. So only one twice the gate is activated. So the value is 0, 1. So which means that we will activate the twice the gate. So which means the y comes up 0, 0, 1, 0. So we can use decoder for this purpose. Also, another example is the memory. Actually, we do not learn about the memory logic, but memory looks like this. So there are many rows, so the rows, and then based on the address, then we need to activate one of rows. So based on input values, so based on input address, then we need to activate one of these multiple rows, right? So this is actually the structure of the memory. Okay? So memory is composed of many rows, and then we need to activate only one of these rows. Okay, row. So for this purpose, we can use decoder. So which means that, as I mentioned, we need to activate only one of the rows. This is the input. So which means that these are activation wires. Activate the connection for activation. That means we can activate only one row. So we can use decoders for this purpose. Okay. So actually, if we just memorize the definition, it's very simple. So how can we implement the decoder? So we can implement the decoder using SOP form. So there are 2 inputs, then there are 4 outputs. And then based on the input values, the only one output becomes 1. So if we just see this output, then we can observe that this Y0 is connected to the not A1 and not A0. So which means that the Y0 equal not A0, not A1. Which means if the A1 is A0 is 0 and then A1 is 0 and Y0 becomes 1. And then using the same way, then we can also implement the Y1, Y2, Y3. Right? It's simple. So Y1 equal it's A0 and A1. So it means that the Y1 becomes 1 if A0 is 1 and then A1 is 0. And then Y2 is not A1, right? It's very simple actually. So actually decoder the output of the decoder is composed of main terms of input ports, input signals. Okay, so it is because actually each output, right? So which means this is the Y0, Y1, Y2, and Y3. So we can observe that these ports are just main terms of A and B. So which means we can also build a simple combinational logic using decoders. Because when we build a decoder, these 4 outputs, the 4 output values are just covers the all possible values of input values like A and B. So which means that this output ports Y includes the all midterms of input signals. And then by connecting midterms, then we can build any combinational logic, right? That's what we learned in the previous class, right? So which means we can build any combinational logic using a decoder. So this is the example. So this is the combinational logic A plus not A and not B. So if we see the this decoder, then we can know that okay means the not A and not B because this is A, this is B, and this is Y0, and this is 0, 0. Also, so we can know that this is the AB. Because this is in the 1, 1. And then by connecting AB and or A bar and B, then we can generate this output, any output. So this is because when you write a build a decoder circuit, then actually this is the Y0, Y1, Y2, Y3. So which means that by combining Y0 or Y3, and then it's the same to the AB plus not A, not B, right? It's very simple, right? Then so using a decoder, then you can use SOP form, combinational logic. Okay. And decoder is very simple. I believe you can easily understand the decoder. Okay, then let's see how to implement decoder using a system value. So also it's very simple. So we can define the output based on the input values. So which means that we can implement decoder using this statement, right? So this example shows the so-called decoder. So Y is the 4 bit, and then A is the 2 bit signals. So based on the A, the 0, 0, 0, 1, 1, 0, and it 1. Okay, actually it means the 1, 1. But I said that it's good for use. It's good for using involved in a case statement, not to avoid critical bugs. Okay. So actually this means the 1, 1, but we can use the default here. And it's a good practice for system value coding. So, and then it's simple. And then based on the input signal, the output Y is defined. So if we input signal is 0, 0, well, output Y is the 0, 0, 0, 1. Then 0, 0, 1, 0, and then 1, 0, 0. So actually it's same to the truth table, right? It's very simple. So we can easily implement a decoder using case statement, right? I think it's you can easily understand how to implement decoder. So it's just one page. Okay, so that is the decoder. So actually, for the basic building block, so we learned about the multiplexer and then decoder, and so those are very important combinational blocks. And then also, it means that these blocks are frequently used in the normal digital logic. Okay. Now, let's discuss about timing of combinational logic. What is timing? So actually, until now, and then I believe you can remember this figure. Then this figure explains about the components of combinational module, right? And then I explained that a module, a digital module, includes the input ports, output ports, and then functional specification and time specification. Those are four components of digital module or this combination module. And then until now, we learned about these three components, right? So inputs are just defined, outputs are defined, and then functional specification. That is the Boolean equation defined by input and output values, right? Those are what we learned until now. And then only this component is missing, the timing specification. So I did not explain about the timing specification yet, but when we define a combinational logic, we also need to consider time, which means that delay of combinational logic. So what does that mean? So actually, I repeatedly say that is the logic, but is the hardware works in real world, and the real world includes the time, right? So which means that if this looks this diagram looks like a black box. So input value is given to this black box, then output values are generated, but after some delay delta t. Okay, so after some time. It is because we can implement a digital logic using CMOS transistors. Then which means the CMOS transistors are actually electric circuits. And then when the electric circuits, the values or signals in electric circuits are changed, it is changed after some delay. It is because electric circuits includes the resistance vector and capacitance vector, and then resistance and then capacitance in electric circuits combines delay of this circuit. So it is actually it's obvious. So we can build combinational logic using CMOS transistors, which means electric circuit, and then electric circuits includes the resistance factors and then capacitance factors, and then these factors determine delays of circuit. So we need to also define the timing specification of a combinational logic or digital module. Okay, so let's see this example. So this is the just buffer, and this is input A and input output Y. And then we already know the functional specification of this buffer. Okay, so Y is just the same to the A, right? It's the functional specification. But in this buffer, we need to also consider timing specification, which is also delay of the circuit. So what does that mean? So A, the value of input signal is changed from 0 to 1. Okay? And then if the Y is equal to A, now this is the functional specification of the buffer. And then if this block is an ideal block, then if there is no delay, so Y is just equivalent to the A. Y should be just equivalent to A. But in real world, this circuit has delay, the timing specification. So actually, Y is changed after some delay. This amount of delay is delta t. So if you see this waveform, okay, the waveform, the output, the waveform of Y is different from the waveform of A, right? Even though the function is Y equal A is equivalent, but if we just consider the timing of this buffer, because of the delay, the waveform is different. Okay, so we need to also consider this delay, the timing part of the circuit, when we build this top module, which is very important. Sometimes, so I believe you are very familiar with the software coding. But when you write a code, then we don't need to consider about this delay. So we think that when the code is just executed, then the output is immediately determined based on the input values. Right? That is the illusion. This means that it's not true actually in the real hardware, but in software, when we use software, when you write the code in programming languages, then we can think that the output values are immediately determined by input values. Okay, that's some software perspective. But when we consider the hardware, then we need to also consider this delay, the timing factor, the timing specification of the circuit. So actually, even though this means the y equal a, it means after some delay, the the value of y is changing based on the input values. That's very important. So actually, when we design a buffer, this is the time this is the functional specification. And if we see this equation, the y equal a, we can think that y is just equivalent to a. That is the software perspective, but it's not true because it's a hardware. So which means that the value of y is changed after some delay if a is changing. Okay, so we need to consider the timing specification of a circuit. Okay, it's very important. Because sometimes we just ignore the delay from our circuit because we are very familiar with the software coding. But when we consider hardware design, then we need to also consider this timing specification or timing behavior of our design. Okay, there are two kinds of delay. So when we consider the delay of the this module, so this delay is called the propagation delay and contamination delay. So actually, so I believe so it's a new concept because as I mentioned, I believe you are very familiar with the software code like y equal a, and there is no delay. But I said there are delays. Is the circuit, but there are two kinds of delays, like propagation delay and contamination delay. Okay. So propagation delay means that it's the maximum delay from input to output. And then contamination delay is the minimum delay from input to output. So what does that mean? Why? Why there are two kinds of delay? It's just the buffer, right? So y equal a. It's just the buffer. But we need to consider the two different delay values, like max delay and minimum delay. Okay? And then simply we can say that this is the maximum delay, the propagation delay, and then this is the minimum delay of this circuit. Why? So it means that when the A is changed, then Y can be changed at the TPD, so propagation delay, or when the value of A is changed, the Y can be changed after contamination delay, so minimum delay, TCD. So which means that in circuit, the Y is changed between this timing window. Okay, so that's because there are two kinds of delays. Why? Why is it so complex? It's not simple, right? So even though when we consider about the delay, it's not easy, but we need also consider the two kinds of delay in the circuit. So there are many factors that determine the propagation delay, the maximum delay, and the contamination delay, the minimum delay. So as I mentioned, the delay of a circuit is determined by capacitance and resistance. Okay, the capacitance factors like capacitor and then resistance. And then why? Why there are two kinds of delay, propagation and concatenation delay? It is because this is the first reason. Different rising and falling delays. What does it mean? So actually, when we consider the input signals like A, the input signal can change from 1 to 0. So this is the falling, right? Because the signal was high, and then signal is changed to low. So it means the falling. So falling. And then also the signal, the input signal can change from 0 to 1. So it means the rising. Because the change from low to high. Okay, so rising delay. But when the input is changed from 1 to 0, it's falling. And then if the input is changed from 0 to 1, the delay of circuit is different. So that's the main reason. Why? Oh, it's very complex. Actually, the real world system is very complex compared to the fantasy world system like software. So why? So it is because we need to build digital logic using CMOS transistors. So for example, this is the inverter, like this is the A, and then A is connected to actually two different transistors. Two different transistors. Like here, this is the output, right? And then actually there is a capacitor here. This is the parasite capacitor, pure capacitor. For using this capacitor, the Y, the value of Y is determined. So, so actually, when the Y, so when A is changed from high to 0, it's 1 to 0, then Y is changed from 0 to 1. Because it's in an inverter circuit, then it means that the electric, actually this PMOS transistor is activated, it's turned on, then electric charge is stored in this capacitor, and then this behavior is determined by PMOS transistor, right? And then other behavior, if the A is changed from 0 to 1, then Y is changed from 1 to 0. So in this case, this NMOS transistor is activated, so which means that the Y is connected to the ground. So electric charge stored in this capacitor is just dissipated to ground. Okay, it's moved to the ground. So which means that this behavior is determined by NMOS transistor. Okay, so actually in the real digital circuit, this change of output value like 1 to 0 and 0 to 1 are determined by different transistors, like PMOS transistors and NMOS transistors. And these transistors have different characteristics. Okay? So it means that the rising and falling delays are also different even in this circuit. Okay? Because the rising in this inverter, this is the inverter, the rising of this output is determined by PMOS transistor, and then the falling of output value is determined by NMOS transistors, because the different kinds of transistors are different kinds of transistors influence the output Y. So which means that the rising and falling delays are different. CMOS circuit. That's the main reason, actually. Okay? The rising and falling delays are different. So which means that when we actually the actually the semiconductor which means that the fabrication companies such as the TSMC or Samsung, so it just actually provides the basic libraries for the basic gates and then also multiplexer and some other basic blocks. And then they actually just define the different rise and falling delays. So which means that when a combinational logic is defined, so which means that we need to define timing specification. So which means when they provide the basic gates, it's called the library. So basic gate libraries, they also need to provide the timing specification. But because of this reason, they provide the different rising and falling timing specification in their library. Also, another reason is that there are multiple inputs and then multiple outputs in our combinational logic. And then actually, when we design a combinational logic, there are many internal nodes. Okay? So which means that from the output to input path, there are different numbers, different counts of gates. Okay, so that's why the delays are different of this output. I will show the example of this the next slide. Also, the characteristics of resistance. So these resistance factors and then capacitance factors can be changed by temperature. Okay, so which means actually, I believe some of you remember that Samsung. I forgot the name of the gate. So which means that Samsung adjusts their HP, the application process, and then they slow down the performance of their mobile processor, right? They adjust the mobile processor. Is it because temperature? So, which means that the delay is low, so which means that the performance is low. And then if the delay is short, then performance is high. So this performance is also influenced by temperature. Okay? And then if we just play game using our smartphone, then our smartphone becomes hot, right? Its temperature is changing. So actually, we have to avoid some critical temperature. Samsung just limit the performance of their mobile processor. I forgot the name of the game, but so this is because of temperature. Also, if temperature is changed, the delay is also changing. So which means that if the temperature is high, which means it's hot, then the delay is increased, it's slow down. So it's slow down, then hot, which means the delay is increased, and if the socket is cold, then delay is increased. Also, which means that this determines the maximum delay and minimum delay of a circuit. Okay, and then also there can be process variation or voltage variation. Actually, the delays are determined by temperature and voltage and process. The voltage level also can be changed in our circuit. So this voltage also determines the delay of the circuit. So because of these many factors, the circuit has the different delay and propagation delay and information delay. Okay, I think it's a little bit tricky, but it's real. So in the real environment, we need to consider the delay. But delays are determined by many factors. Okay, so let's see some different paths in the delay calculation. So this is the example. So Y is determined by 4 inputs A, B, C, and D. And then, as you can see, and the Y is determined by A, and B. Then these input signals need to pass through 3 basic gates. AND gate, OR gate, and AND gate. And then these are combinational logic, so which means that this logic also has the delay, like delta t, and delta t. Okay? So which means that if the the output y can be changed by input signals A and B, right? So if y is changed by input signals A and B, then we need to consider these delays, the delays of these combinational logic. And then which means that these delays need to be accumulated. But y can be also determined by t, because this is the AND gate, and if t is changed from 1 to 0, right, then y is also changed from 1 to 0. If we see this path, output y is just, if y is just determined by b, then it doesn't get through one large gate. So, which means that when you just consider the number of combinational logic in between the output and input path, this path just pass through one combinational logic, but this path just pass through 3 combinational logic, combinational gates. Okay, and then we can check that, and then obviously it will take longer, right? Because the input signals pass through 3 logic gates. So this becomes the longest path, or it's also called the critical path. It's the longest path in this circuit. And then in this combinational logic, the max delay can be calculated like this. So this is the propagation delay, the maximum delay of the circuit from one of the input signals. It's the propagation delay of AND gate, and then propagation delay of OR gate. There are 2 AND gates here. So 2 multiplied by TPD of AND, and then plus TPD of OR. So we can simply calculate the maximum delay of the circuit like this. Okay? And then, this is the shortest path. So because there is one basic gate between Y and P. So contamination delay of the circuit is equivalent to the contamination delay of this AND gate. Okay, so as I mentioned, the multiple input and outputs, and then also there are multiple nodes and different number of different counts of basic gate. So the delays are also changed by this spectrum. Okay. So we can define the longest path, the critical path, from input output, so we can define the shortest path. understand? Okay, so then let's learn about the glitches. So what is a glitch? So glitch means that this is the continuous signal, right? But if we can observe some changes like this, which means that the signal is this is the time, and this is the signal value, and then at the time the signal is just continuously high, but it changed like this. Okay, so and then this is called a glitch. Okay, which means that actually we expect that the output signal of a combination logic will change like this, like 1 to 0 or 0 to 1. So which means that once a value is changed, the changed value is maybe is kept for some time. For some time. But glitch means that the value of the output signal changes like this. Okay? So we can actually we expect that the output value is like this. It's continuously 1. But by some reasons, the output is changed like this. So 1 is changed to 0, and then after short time, the value is changed from 0 to 1. This is called a glitch. Then let's see the example of glitches. This is the circuit. So what will happen when A is 0 and C is 1 and B false? So A is 0. A is 0 and then C is 1. So which means that this is the B, right? Because this C is 1 and this is the AND gate. Also because the A is 0, then this is 1, and then this is the B bar. Right. And then if you see the Y, and then Y is the B bar or B, and this is 1, right? This is the combination of Boolean theorem, right? So if B changed from 1 to 0, okay, and then this Y is not changed because of Boolean theorem, then and then the A is 1, and then this is the AND gate, the B bar, and then another AND gate is B, so Y is just 1. Okay? But we can observe glitch here in this circuit. It is because actually A is 0 and C is 1, and then B false. So input changes. So which means that the signal value of B is changing. And then which means that Y can be the value of Y can be changed by input value B, because B is changing and B is the one of inputs. And then which means that if we just see the Y, so there are two passes determined by B, so this pass and this pass. Okay? And then we can observe that for this pass, there are three gates, like not inverter and AND gate and OR gate. And then if we just see this pass, the lower pass, then we can just observe two gates, which means the delay can be different from this upper pass and then lower pass, because for upper pass there is an inverter. So this is the difference. Then what will happen? it becomes the critical path, and then this is the short path. So if B is changed from 1 to 0, so we can say that the N2 will be changed, right? So this is 1, so which means that this is B. So but after some delay, N2 node is changing because of this delay of this AND gate, right? So the N2 value is changing after some delay, okay, after some time. And then if we just see this N1 node, so if we just see the N1 node, so this is the not B, so which means that the if B is changed from 1 to 0, and then the not B is changed from 0 to 1, right? But we can observe not gate here and the gate here. So which means that we can expect that the delay of N1 is longer than the delay of N2. Okay? Delay at N1 is longer than delay at N2. Right, obviously because there are more gates. There's an not gate here. So if we see the waveform of the N1, then N1 is changed like this. Okay? So this is the OR gate. Then if we see this is and then Y is the output of OR gate, then the inputs of this OR gate are N1 and N2. So this is the waveform, and this is the waveform. And then until this time N2 is 1 and N1 and 1 is 0 and N2 is 1, right? So which means that this Y is the 1, right? But after some delay. And then if we just focus on this time, this is 0 and this is 0. So two inputs of this OR gate are all 0. So Y becomes 0. Okay, after some suppose this is reflected after some time, right? Some delay of this OR gate. So that's why the 0 is here. And then after that, this is 1 and this is 0, and then it becomes 1. So with the Boolean equation, we already know that Y is with the Boolean equation is not B or B, and which means it's 1. Which means that we can expect that Y is not changing, it's just 1, even though the B is changing. And then this is the Boolean equation. But in real circuit, because of the different delay, you can observe that the Y, the value of Y is changing like this. So like 1, 0, 1. So we can observe very short change in this Y. And then this is called a glitch. Okay. So if we just consider a timing of a circuit, a real circuit, then we can observe some different behavior called a glitch. But this is the Boolean equation. It should be always 1, but in reality, the Y can be changed like this, like 1, 0, 1. Okay? So this is the glitch. Okay? So actually, when we consider a timing specification of a circuit, and the system becomes more complex. Okay, because the software just outputs become immediately, but in real hardware, the output is determined at some time, and because of this property, the system becomes more complex. Okay, and then actually we don't like this situation. Okay, I don't like this situation because the system becomes more complex, which means that it's not easy to design a stable or correct system. It is real timing is considered, okay, because the system becomes more complex. So nobody likes this situation, okay? I don't like it, then you don't like it because it's complex. Okay. Then how can you avoid the glitch? We can add the additional gene, which means that additional path. So, you know, why glitch happens in this circuit? The B just pass through this gate and this gate, so which means that the Y is also determined by output of this AND gate and this AND gate. So when B is changed, and then also we can find the different paths or different delay to the two inputs of this Y. So in this situation, Y is determined by B, only B, right? And then actually B goes pass through the different paths like upper path and then lower path. So which means that if Y is determined by other signals except B, then we can avoid glitches, right? So this is the example circuit. So we can just add the AND gate here, and then the one is one gate connecting to this AND gate. And then you can find that this AND gate, the output of this AND gate is determined by A and C, right? It's not B. So and then you know this one, like maybe it's one, always one. Always one. So even though B you change it like this, so M1 is changed like this, and then M2 is changed like this, right? But because of this value, this is always one, so Y becomes always one. So by adding this circuit, this gate, then we can avoid glitch. Okay, but it's not good. Why? Because we need to add more hardware resources, right? It's not good. More hardware resources are added. So I don't like it. We don't like this situation also. Okay. So actually, we discussed about the glitches. So and then we also know that glitches can be removed by adding redundant gate. Actually, this is not required actually, but not to remove glitches, then we can add redundant gate. It's not required, but in order to remove glitches, we can add more gates. But it's very hard. It's very hard to remove all glitches. Okay, it's very hard. So you need to remember, you can remove glitches by a redundant key. It's possible, but it's very difficult. It's very difficult. Okay, so it's very difficult. So, and then actually this is the problem of combinational logic. So which means that even in the Boolean equation, we expect that the output value is just kept. Our value is just kept like this, so it's not changing. But because of the different delays, different propagation delay and some other factors, we can observe frequent glitches in the output of combinational logic. So we don't have this situation to get some clean signal. Then we need to add the redundant gate, but we don't like also this situation because it requires more hardware resources. So actually, we use the we employ synchronous design convention, and we will learn in chapter 3. So we will learn about the sequential logic in chapter 3, which means that actually the output of the combinational logic is sample purely. Okay? Because of the glitch, we cannot get clean output from the combinational logic, and then it can be a serious problem or serious issues in the real digital circuit. But everyone wants to get clean result from the input signal. So we use synchronous design, or sequential logic. We can build the synchronous logic using the sequential logic. Okay, then we can ignore glitches. Okay, this is very good news, right? Because of the glitch, we cannot get clean output from the combinational logic. But if we build the synchronous logic, synchronous design, then we can ignore glitches. Okay, that's why we need to learn about the sequential logic. Okay. Okay, so this is the problem. We cannot remove all glitches. So we will use the synchronous design. Okay. Okay. And then actually the old digital design are synchronous designs. Okay? Synchronous systems. Which also same for the CPU design. The CPU design works with the clock signal. So which means that if a certain design uses a clock signal, then this is called a synchronous design. Okay. Okay, so please read the textbook. Okay, and then this is another topic. Delay in system value. Okay, we have just 10 minutes, but I believe I can cover delays in system value within 10 minutes. Okay, so we learned that our module needs to include the timing specification to delay, right? So which means the system value was just used for simulating or exercising our audio design. So which means that system value also needs to reflect the time specification of our audio design. Because it's a hardware design, and then system value is used for hardware design, which means that system value also needs to reflect the time specification of our hardware module. So this is the test bench code of the period number M2, and then you can find that sharp and number here. So actually in this test bench code, sharp and number represent the delay. Okay, and then also you can find the time scale here. So this is the just definition. So it's very similar to the definition of C. And then time scale means that in this system value we will use delay, and then time scale just set the unit of the delay, time scale unit, and then resolution, the possible resolution. So which means that in this test bench code, I set time scale as 1 nanosecond and 1 picosecond. And then this is the delay. I just use the number, not the time unit. So which means that, so I said that this is the time scale unit, and then this is the time. So which means that it's the delay, and the delay is 10 nanoseconds. Okay? Because this is the time scale unit. Which means that in this code, we use the nanosecond, 1 nanosecond as the default time unit. Okay? So the 10 nanosecond. Then what is the resolution? The resolution is the picosecond. So which means that in this code, I can define until 10.001. So this is the picosecond. So which means that we define the resolution of the time delay in system level code as the picosecond unit. So which means that if we write a time, if we define delay of this line like the 10.001, then it's okay, because the resolution of this system value module is defined as the 1 picosecond, but it's not allowed like 10.0001, because this is the 0.1 picosecond, right? So, and then actually in this code, I said 1 picosecond is the resolution of the time unit. So this is not allowed. Okay. So actually in the test bench, I just use the delay. And then so this delay is that after 10 nanoseconds, A becomes 0. And then B becomes 0. Okay. This is just the delay. So in the system value, we can also define delay of signals. So this is another example. So after the assign statement, we can add the number here with a sharp 1. So then this defines the delay. So what is the assign statement? If this right hand side signals are changed, the left hand side signals are also continuously reflected by changes in these signals. Okay? But if we define delays in the system value like here, it is reflected after this delay. Okay, that is how we represent delays in system value. And then as you can see, this time scale is also defined here, which means that the delay of this logic is the 1 nanosecond. Okay? But you need to remember that delays are just for simulation only. Okay? So we design our audio module for simulation and synthesis, but this delay cannot be synthesized. Delay is only reflected in simulation. Okay? You just remember this. It's not. So actually, even though we just set the delay like 1 nanosecond here, when this project is synthesized, this delay is not reflected in the synthesized module. Okay? Delays are for simulation only. So you need to remember this. Right? Okay. So you can define delay like this. Then let's see the example of delay in system value. So actually, initially all signals are unknown. Okay? Unknown in the system value. And then after that, after some very shortly, then the system, the values of these signals are determined. So for example, so look at this. Actually, this is the initial means the just start point. At start point, A is unknown, B is unknown. But I just initialized the A and B like 0 and 1, like this. So if you see the waveform of this circuit, then you can find that A is here, and B is here, and C is here. But you can observe very short changes in A and B and C, right? So firstly, A, B, C are unknown, but after that, it becomes 0. Okay. But if you see this assignment A, B, 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 and C, B, then delay is 1. So what does that mean? This is just not A, B, C, but after 1 nanosecond, these outputs are just determined by input signals after 1 nanosecond. So you can observe unknown values here, okay, for 1 nanosecond. So the output is just reflected after 1 nanosecond. And then, the N2 is determined by A, BB, and CB, A, BB, and C. So, the BB, BB, and CB are determined at the 1 nanosecond, at the starting point. So, which means for the N2 and N3, so, sorry, actually, this is the AND gate. Okay, so and then the A is 0 and B is A is 0 here. But this is the AND gate. So actually, if A is 0, then the N2 and N3 also becomes 0. But BB is unknown and C unknown, but the output N2 and N3 are determined by A, right? But after 2 nanoseconds. So because of this, the N2 and N1 and N2 are determined. This is N1, N2 and N3. Sorry. N2 and N3 are determined after 2 nanoseconds because of A. Because A becomes 0. And then these changes are reflected after 2 nanoseconds. And then if we see the N1 is determined by AB, BB, and CB. And AB and BB and CB are determined by ABC at the 1 nanosecond. Then N1 is determined by AB, BB, CB after 2 nanoseconds. So AB, BB, CB are determined at this point, and after 2 nanoseconds, N1 is also reflected. So N1 becomes after 3 nanoseconds, the N1 is determined. Okay, so you can calculate the N4 like this. So this is the delay. How to represent delay in the system value. So using the sharp and number, we can represent delays our system value design. But delays are just for simulation only, okay? Just for simulation only. So we can just represent the delay in the system value like this. Okay, so this is the. Then also you need to read the chapter 4.3 and 4.5 for the system value part. Okay. Okay, so I'll stop here. Any questions? See you in the. Okay, good luck for the video. 감사합니다.